Thank you, Lucas. First of all, I would like to thank all the organizers, Lucas and Jaime, for the invitation. For me, it's a great pleasure to be here. My first time talking in the Colóquio, the Brazilian Colloquium of Mathematics. So I'm very happy for that. So as Lucas said, today I'm going to talk about initial data rigidity results, or initial data sets rigidity results. This is a joint work with Michael Eichmer and Greg Galloway, which is going to appear in Communications in Mathematical Physics. Okay, so in this lecture, we aim to present some rigidity results for initial data sets that are motivated by the space-time positive mass theorem. So let me start by remembering some definitions. An initial data set, MGK, consists of a connected Riemannian manifold, MG, and a symmetric 0 to tensor K. So although not required for all results we are going to state or present, we are going to assume that M is oriented for simplicity. The local energy density, mu, and the local current density, J, of the initial data set are defined in this way, okay? So here, R is the scalar curvature of the Riemannian manifold. We say that the initial data set satisfies the dominant energy condition if this inequality this inequality here holds on the manifold M, okay? Now let sigma be a closed two-sided hypersurface with unit normal nu, and H be the mean curvature of sigma in M, which means that H is the divergence of the vector field nu with respect to sigma. Then we can define the null expansion scalars, or the null mean curvatures, theta plus and theta minus of sigma, in the following way. Okay, so theta plus is H plus the trace of K with respect to sigma, and theta minus is H minus the trace of K with respect to sigma. Also, we say that the hypersurface sigma is outer trapped if theta plus is negative, weakly outer trapped if theta plus is non-positive, and marginally outer trapped if theta plus vanishes. So in the latter case, we say that sigma is a marginally outer trapped surface, or MOTS for short, okay? Also, we can consider two quantities, chi plus and chi minus, defined by chi plus equals A plus K restrict to sigma, and chi minus A plus K restrict to sigma, where A is the second fundamental form of sigma in M. So our sign convention is such that H, the mean curvature, is exactly the trace of the second fundamental form, okay? In this case, theta plus, the null mean curvature, theta plus equals the trace of chi plus, and the same for chi minus is the trace of chi minus. Oh, sorry, theta minus is the trace of chi minus. All right, so I have to say that initial data sets arise naturally in general relativity. So, for example, let M bar G bar be a space-time, which means that it is a Lorentzian manifold, a time-oriented Lorentzian manifold, and M be a space-like hypersurface in the space-time M bar. And denote by G the Riemannian metric induced on M, and K the second fundamental form of M with respect to the future pointing unit normal U of M in the spacetime M bar. Then MGK is an initial data set. In fact, we can prove that, for example, if M is compact, that's always the case. So we always can assume that M is embedded the initial data set is embedded in this way in a space-time. Now consider a closed two-sided hypersurface, sigma and M. So in this setting, chi plus and chi minus are exactly the no second fundamental forms of sigma in the space-time M bar with respect to the no normal fields defined in this way. So L plus equals nu plus u restrict to sigma, and L minus equals nu minus u restrict to sigma. So that's the general picture. All right. An initial data set, MGK, is said to be time symmetric or Riemannian if K vanishes. In this case, the dominant energy condition is just the requirement that the scalar curvature Mg of the manifold, the Riemannian manifold, be non-negative. So in this case, sigma is a mod if and only if it is a minimal surface. Because that, it's not surprising that marginally outer-trapped surface share many properties with minimal surface, which they generalize. So, for example, mods admits a notion of stability based on variation of the no expansion due to Anderson, Mars, and Simon. Also, mods admit a existence theory due to Shen and Yao, Anderson and Metzger and Eichmann. We are going to use this result in the proof of the main result here in this lecture. Also, we say that a separating mod is weakly outermost if there is no outer trapped, so surface satisfying this, surface outside of and homologous to sigma. So let me make a simple picture here. So suppose we have our manifold M. So here is our manifold M, and we have a hypersurface sigma. And let's call this side the outside of the manifold of the hypersurface. Okay, so this is the outside of sigma. Then we say that sigma is weakly outermost if there is no hypersurface here homologous to sigma and in the outside of it with negative no mean curvature theta plus. Okay. We also say that a mod is outermost if there is no weakly outer trapped surface satisfying this outside of and homologous to the hypersurface sigma. All right. Okay, now let me state the space-time positive mass theorem, which says the following. So this theorem is was proved by Eichmann, Huang, Li, and Shen, and it says the following: let MGK be an n-dimensional asymptotically flat initial data set with ADM energy momentum vector EP. Assume that the dimension is between 3 and 7, and it also satisfies the dominant energy condition. Then the energy is not less than the length of the momentum vector P. Okay, so in broad terms, the proof of this theorem generalizes to the space-time setting the proof of the Riemannian, which means K equals 0, positive mass theorem by Shen and Yao, where now mods play a role analogous to the minimal surface in the Shen-Yao's proof. So this shows the importance of the marginally outer-trapped surface. All right, but in this lecture, what is important for us is that Locamp has presented a different proof of the positive mass, the space-time positive mass theorem in all dimensions. So, and his method is by reduction 2 in the proof of the following theorem. So Locamp proved that the space-time positive mass theorem is equivalent to this the following result. So let MGK be an initial data set that is isometric to the Euclidean space with K equals 0 outside some bounded open set. So this is the general picture. So here is the outside of U, and we are assuming that K equals 0 outside U, and M is isometric to the Euclidean space, okay, outside U. Then one cannot have this inequality here on U. So that cannot happen. Sorry. But what we are going to show is that a much stronger conclusion holds in dimension between 3 and 7. Okay, in particular, our result implies the Locamps result. In particular, using the reduction proved by Locamp, our result implies the space-time positive mass theorem. Compactifying the Locamp's picture, we obtain a compact initial data set, MGK, with boundary. So the boundary has two components. One we call sigma naught, and the other one we call S, okay, where sigma naught and S are flat n-1 tori in MG, and both are totally geodesic in the space-time sense. So the no second fundamental forms vanish altogether with respect to either choice of the unit normal. In particular, both are mods, okay? So here is the Locamp's picture. We can take a big box and identify all but one side of the box, or two sides, opposite sides. All right. But to be a little bit more general, we are going to assume different hypotheses in our theorem. So the first one is what we called the cohomology condition. So in our result, we assume that sigma naught satisfies the cohomology condition, which means that there are n-1 classes in the first cohomology group whose cup product is non-zero. Observe that the dimension of sigma naught is exactly n-1. So by Shen and Yao, if sigma naught satisfies the cohomology condition, then it doesn't admit a metric of positive scalar curvature. In particular, the n-1 torus, or more generally, the connect sum of the n-1 torus with some orientable and closed n-1 manifold satisfies the cohomology condition. Another hypothesis we are going to assume is that M satisfies what we call the homotopic condition with respect to sigma naught. For example, this condition holds if M has almost product topology. So if M is diffeomorphic to a manifold like this, okay? Or more generally, if there is a retraction of M onto our hypersurface sigma naught. All right, just some technical hypotheses in topological hypothesis. But it's important to say that under the cohomology and the homotopic condition, every surface sigma homologous to sigma naught also satisfies the cohomology condition. So in particular, by Shen and Yao, it doesn't admit a metric of positive scalar curvature. So in our picture, if we have here is the boundary, one component of the boundary, the other component must have more than one component. And if sigma is a hypersurface homologous to sigma naught, and sigma naught satisfies the cohomology condition, and M satisfies the homotopic condition with respect to sigma naught, then sigma also satisfies the cohomology condition. In particular, sigma doesn't admit a metric of positive scalar curvature. All right. Then we have our first result of this lecture, which is theorem A. So the theorem says the following: let MGK be an n-dimensional, n between 3 and 7, compact with boundary initial data set. So suppose that it satisfies the dominant energy condition, and the boundary can be expressed as a disjoint union of hypersurfaces, okay, like this, such that the following conditions hold. So the first one is that the Nome curvature theta plus is non-positive along sigma naught with respect to the normal pointing into M. So this normal here, okay, it is pointing to the inside of M. Theta plus is non-negative along S with respect to the normal pointing out of M. And also we have the topological conditions. So the sigma naught satisfies the cohomology condition, and M satisfies the homotopic condition with respect to sigma naught. So remember that in the low-campus picture, this hypothesis here is trivial, okay? Also, this one is trivial because we have equality here in low-campus picture. Then M is diffeomorphic to this product. And each leaf of the foliation produced by this product is a mod. In fact, each leaf has vanished no second fundamental form, chi plus. Also, it is a flat torus, and we have this equality here on M, and mu restrict to sigma equals 0. So because this condition here, okay, we obtain low-campus theorem. So low-campus theorem follows because this condition. Then in particular, it can be like this inside of the open set, okay? All right. Then let me make some comments on the proof of this theorem A. The proof consists of 3 elements. The first one is showing that sigma naught is a weakly outermost mod. Remember that we are assuming that theta plus is less than or equal to 0, but we are going to show that sigma naught is in fact a mod, so it is a mod and weakly outermost. After that, we use a rigidity result by Greg Galloway for weakly outermost mods to obtain a neighborhood of the boundary sigma naught on which the conclusions A, B, and C of the theorem hold. Then finally, we extend this neighborhood to all of the manifold M. Okay, that's the idea of the proof. All right. So as I said, the first step is showing that sigma naught is a weakly outermost mod. So let's see. Okay, so assume for the moment that sigma naught is a mod, okay? Then we want to show that if sigma naught is a mod, it is weakly outermost. So suppose it's not. Then by definition, because it is not weakly outermost, there is a hypersurface homologous to sigma naught, okay, with negative no mean curvature theta plus. All right, now we can consider the region bounded by sigma and S. The other S is the remaining components of the manifold. So denote this region by W, and now change the time orientation of your space-time, which means that we can change the sign of the tensor K, all right? Then we obtain this initial data set satisfying this hypothesis here. But a classical result due to Shannon, Yao, Anderson, Metzger, and Eichmer says that under this condition, there is a outermost mod, sigma naught, sigma prime, homologous to sigma, okay, in the initial data set W, okay? But because sigma prime is homologous to sigma and sigma is homologous to sigma naught, sigma prime is homologous to sigma naught, and by the cohomology and the homotopic conditions, we have that sigma prime doesn't admit a metric of positive scalar curvature, which contradicts the following result by Greg. So the Greg's result says that if you have an initial data set of dimension n greater than or equal to 3, satisfying the dominant energy condition, and you have a outermost mod, sigma prime, then it has to admit a metric of positive scalar curvature, okay? Then we get a contradiction. In this case, if sigma naught is a mod, it has to be weakly outermost. Now, suppose that it's not a mod, all right? So if it's not a mod, then sigma theta plus has to be negative somewhere. In this case, we can use an argument due to Anderson and Metzger to perturb our surface a little bit and obtain a strictly outer-trapped surface outside sigma naught and homologous to it. Then we can run the same argument again to get a contradiction. That's the idea of proving this lemma. Okay. All right. Then now we know that sigma naught is weakly outermost and doesn't admit a metric of positive scalar curvature. Then we can apply the following local rigidity result by Greg. So assume that you have an initial data set satisfying the dominant energy condition, and suppose sigma is a weakly outermost mod in the initial data set that doesn't admit a metric of positive scalar curvature. Then an outer neighborhood U, okay, diffeomorphic to this product of sigma, a outer neighborhood of sigma in M is foliated by mods, which means that each leaf of this foliation is a mod. In fact, he proved more. He proved that each no second fundamental form chi plus equals 0 along sigma t along the leaf. Sigma t is rich flat, and we have this equality here on sigma t. Okay, so this condition is exactly the same as in theorem A. So we are done at least in a neighborhood of our boundary, so sigma naught. This one is a little bit different because we want to prove that sigma t is in fact a flat torus, and this one also is a little bit different. But how to obtain that? So to obtain that, we use Greg's condition here, okay, C, and the dominant energy condition. Make some simple calculations to obtain this. It's not difficult, just some calculations. And also because we know that sigma t is rich flat by a classical result due to Bochner, we know that the first best number of sigma t is less than or equal to the dimension of the manifold, with equality if and only if sigma t is isometric to a flat n-1 torus. But our cohomology condition implies that the first best number is not less than n-1, the dimension. So then we are done. We have a flat torus. All right. Then we know that our theorem holds in a neighborhood of sigma naught. Then now we want to extend. How to do that? To extend our theorem to all of the manifold M, we can show that sigma t, this foliation converges smoothly to a mod sigma delta as t goes to delta. Okay, then using a surgery argument due to Anderson and Metzger, we can show that sigma delta is in fact embedded, then we are done. We can run the same argument and extend the neighborhood U. Okay, that's the general idea. It's not a proof, in fact, here, but the general idea of the proof. All right. Then we finish proving theorem A. Okay, so, but if we want to say something more about the initial data sets covered by theorem A, we have to impose some extra condition, because suppose we have consider the box, unit box B, okay, in the t equals 0 slice of the 4-dimensional Minkowski space, and consider a smooth function defined on this box, which vanishes near the boundary of the box and whose graph is space-like. Okay, here we can see the picture. And now let M be the manifold obtained from this graph by identifying opposite sides in the X and Y coordinates of the box, of the Minkowski space. Then we obtain a manifold diffeomorphic to this product, okay, to the 2 torus times the closed interval. And we can consider the initial data set, MGK, where G and K come from the induced matrix and the second fundamental form of the graph of the function f in the Minkowski space. It's not difficult to show that MGK satisfies all the conditions of theorem A. Then it has to satisfy also the conclusions. In fact, we can intersect the graph of the function f with the null hypersurface HC given by these equations and obtain a foliation of our manifold. So here we can see our foliation, and it's possible to prove that this foliation satisfies all the conclusions of theorem A. So because this example is so general, we can't say much more about the initial data set proved by theorem A, okay? So if we want to say something, for example, some rigidity result, we have to assume something more. All right. So the assumption we are going to make is what we call the n-1 convexity of a 0-2 tensor. So we say that a 0-2 tensor P on a manifold, a Riemann manifold M is n-1 convex if at every point the sum of the smallest n-1 eigenvalues of the tensor with respect to the metric G is non-negative. Okay. It's not difficult to see that if P is n-1 convex, then the trace of P with respect to every hypersurface sigma is non-negative. Then we can prove the following result. So let MGK be an initial data set as before, okay? And suppose that it satisfies the cohomology condition, sorry, it satisfies the dominant energy condition and the boundary of M, the initial data set, can be expressed as a disjoint union as before, such that the following conditions hold. So the first one is exactly the same as in theorem A. The second one is a little bit different because in theorem A, we suppose that theta plus is non-negative. Here we are assuming that theta minus is non-negative. And the second condition is exactly the same. And the third one, and the extra condition, is that K, the tensor, is n-1 convex. But to prove two results at once, let me make this hypothesis here. So we the other one all the same. but this one here is the only difference. So theta minus is not less than 2 times n minus 1 times epsilon, where epsilon equals 0 or 1, okay? And k plus epsilon g is n minus 1 convex. Observe that epsilon equals 0 is exactly this theorem, okay? Then we can prove that the manifold, the remaining manifold, is isometric to this work product, where sigma naught g naught is a flat torus. So observe that this manifold here is hyperbolic when epsilon equals 1, and it is flat when epsilon equals 0. The tensor K equals a tensor like this. So A is a function which depends only on the variable t. And finally, we have mu equals 0 and j equals 0 on M, okay? To prove this, let me show the general idea of proving this theorem. So it is possible to show that under our conditions in hypothesis on theorem B, it also satisfies, the initial data set also satisfies all the conditions in theorem A. So because that, just making some calculations, we can show that it satisfies the conditions in theorem A. So it is foliated by mods, okay? So sigma k plus equals 0 along the leaves. All right. But we also, the first initial data set is this one. But we can also take a different initial data set, MGP, with P equals minus K minus 2 epsilon G, all right? And show that this initial data set also satisfies the conditions in theorem A. Then it also has to be foliated, the manifold M is foliated by mods in this initial data set, okay? Now we use the convexity and a maximum principle for mods. So here the leaves has this Nome curvature equals 0. Then we can use a maximum principle and also the convexity condition to show that these two foliations agrees, okay? In fact, agree. So because they agree, we can make some calculations and exploit the fact that they agree to obtain the rigidity we just stated, okay? Then that's the general idea. So because the time I'm going to skip the remarks here I made. All right, then finally, let me show a corollary of this theorem, theorem B, in Riemann geometry. So consider now the tensor K equals minus epsilon times G, where epsilon equals 0 or 1. And observe that the dominant energy condition is equivalent to this inequality here. Okay, so the scalar curvature is not less than minus n times n minus 1 times epsilon. So also this hypothesis here, so theta plus being non-negative is equivalent, because we have this equation here. It's not difficult to calculate because we know the tensor. Then this hypothesis is equivalent to this one. So the mean curvature of sigma naught is not greater than n minus 1 times epsilon. And similarly, this hypothesis here is equivalent to the mean curvature being not less than n minus 1 times epsilon on S. For example, in the epsilon equals 1 case, what we have? So we have a manifold So it could have more than one components in this side, and this one just one component because the topological assumptions. And we assume that R, the scalar curvature, is non-negative. Also, we assume that 8 is non-positive, but with respect to this normal, if we consider this normal, then 8, let me call like in this way, is non-negative. And the mean curvature of S is also non-negative. What we have is a weakly mean convex boundary, okay? Then under these conditions, we can prove this theorem, this corollary. In fact, it follows from our theorem B. So let me state. Let MG be in n-dimensional and between 3 and 7, connect compact Riemann manifold with boundary. Suppose that the scalar curvature of M satisfies the dominant energy condition, okay, where epsilon equals 0 or 1, and assume that the boundary of M can be expressed in this way, okay, such that the following conditions hold. So the first one is that the mean curvature of sigma naught is less than or equal to n minus 1 times epsilon with respect to the normal point inside of M, pointing into M, and the mean curvature of S satisfies this inequality here. It is greater than or equal to n minus 1 times epsilon with respect to the normal pointing out of the manifold M. Also, the topological assumptions, sigma naught satisfies the cohomology condition, and M satisfies the homotopic condition with respect to sigma naught. Then Mg is isometric to this work product, where sigma naught G naught is a flat torus. Okay, just take K equals minus epsilon times G and verify that all the conditions in theorem B are satisfied. All right, just some final remarks. Corollary C bears a similarity to a work product theorem by Crook and Kleiner, in which they assume the corresponding lower bound on the Ricci curvature. So our result generalizes to the scalar curvature setting the Crook and Kleiner result. Also, corollary C, in the case epsilon equals 1, yields a hyperbolic space rigidity result obtained by Anderson, Kai, and Galloway. Let me make some comments on this result. So suppose we have a manifold which is isometric to the hyperbolic space outside a compact set, okay? So B. It is isometric to the hyperbolic space outside some compact set B, and the scalar curvature of M is not less than the scalar curvature of the hyperbolic space. Then they showed that M is isometric to the hyperbolic space. Okay, so our result, corollary C, easily implies this theorem. Finally, we could say that, but the proof of corollary C could be approached via variational methods. That's true, but our methodology has an advantage that we can prove the result treating the hyperbolic and the Euclidean case at once. Because if we, for example, in the Euclidean space, we can take area minimizing hypersurface and run a similar argument to prove corollary C. And in the epsilon equals 1 case, we can take B minimizing, brain action minimizing hypersurface and run similar argument to prove corollary C. But the advantage of our methodology is that we can prove the two cases at once. So that's all Thank you very much for watching.